Welcome to the optical communication course. Today we will learn a intermodal dispersion. So intramodal dispersion, that dispersion occurs in a single mode fiber as well as a multimode fiber. And intermodal dispersion that will occur exclusively on the multimode fiber. Because a single mode fiber it has only a single mode propagating through the fiber. So that's why the intermodal dispersion not occurs in a single mode fiber. But in the case of a multimode fiber, that intermodal dispersion occurs. But there are the two types of a multimode fiber. One, we can say that a step index fiber, okay, step index multimode fiber, and a graded index fiber. Now, so if you compare the step index fiber and the graded index fiber with respect to the dispersion, so graded index fiber is worth and that have the greatest bandwidth of a operation there. Now, why this graded index fiber is good as compared to the step index fiber? Now, if you learn that a dispersion is nothing but a what? A pulse broadening. And in intermodal dispersion, pulse broadening occurs because of that propagation delay difference between the modes within a multimode fiber. Means you can say that a propagation delay difference between the modes, okay, propagation delay difference between the mode in a multimode fiber. Now the definition itself is saying that there is a propagation delay difference between the modes, okay, that is difference between the mode in the multimode fiber. So that's why there will be a dispersion. So means no dispersion if we are using a single mode fiber. And sometimes this intermodal dispersion is called as a modal dispersion or a mode dispersion. Sometimes some people are saying it is about a modal dispersion, or we can say that it is about a mode dispersion because various modes are there, and because of that modes, that dispersion occurs. So that's why it is called as a mode dispersion or a modal dispersion there. Now, why this pulse broadening occur? Because there is a difference of a frequency component as well as a difference of this modes here. So multimode fiber, if you see that if we are using a step index fiber, they have the large amount of dispersion because a pulse broadening in the multimode step index fiber is high. So that's why intermodal dispersion occur in a step index fiber is high. But why it is high? Because of that refractive index profile. Now if you consider the step index fiber, the refractive index profile is a constant throughout the core. And in the case of a gradient index fiber, that refractive index profile is the different here. So we can reduce that intermodal dispersion. How to reduce that intermodal dispersion? By reducing the refractive index profile. Okay, by changing or by using an optimum refractive index profile, and so that we can reduce the intermodal dispersion. Now, in the case of a strip index fiber, that refractive index profile is a constant throughout the core. So that's why we doesn't have a scope to reduce the refractive index profile. But in the case of a gradient index fiber, if you choose a refractive index profile, that will be in a parabolic shape. Okay. So in that case, for a parabolic profile, okay, for a parabolic profile, we can use that refractive index profile that is a parabolic one. So in that case, we can reduce the intermodal dispersion. So if you compare the strip index fiber and a gradient index fiber, so pulse broadening in case of a gradient index fiber is small as compared to the pulse broadening in a step index fiber. Means step index fiber, step index multimode fiber have the highest or greatest value of a pulse broadening. So due to the pulse broadening, there is effect on what a bandwidth. Now if you consider the multimode fiber, a step index fiber, because pulse broadening is large, so bandwidth they have the limitations on the bandwidth. But if you consider the gradient index fiber, because pulse broadening is low as compared to the step index fiber, then bandwidth will be increased here. So means bandwidth will be high when we use a gradient index fiber. Okay, if we use a gradient index fiber, then bandwidth will be high there. So as we say earlier, that is, no pulse broadening or no dispersion occur if we are using a single mode of operation, because they have only a single mode there. Single mode is present in a single mode fiber. So that's why there is no single mode operation. Now we'll compare why this pulse broadening is a greater in a step index fiber as compared to the gradient index fiber. So we'll see one by one. A multimode step index fiber. So if you see the multimode step index fiber, so internal structure of a multimode step index fiber, that core diameter as compared to the single mode fiber is large. But if you see that how your rays are propagating through the fiber, so this one is nothing but the axis of a core here. And we can see that rays are propagating through the fiber, and that rays makes that angle with respect to a core and cladding boundary, that will be greater than the critical angle. So likewise we say that supposed to be this one is about a critical angle. Then and then rays are propagating through the fiber. Now some of the rays are propagating. This is about a incoming rays we say here, and this angle makes with the, that will be a acceptance angle of the fiber, and with respect to this one is about a air, and for this air it has a refractive index profile is 1, and a core is a refractive index n1, and cladding it has a refractive index n2. Now that rays are propagating through the fiber, they have the multiple path, okay, as per the numerical aperture or whatever the acceptance angle that rays are propagating through the fiber, they have the multiple path, and some that path, it can be a axial path also. Some of the rays can propagating through the axis, and some of the rays are propagating through the, that reflecting through the boundaries of a core and cladding. So that these rays, those are propagating through the axis, so that is called as the axial rays. and those are propagating through this, okay, reflecting through the core and cladding boundary, that is called as a meridional ray, because they have the a critical angle that we say they are satisfying with the critical angle. Because if you consider that is at a critical angle, that rays are propagating through the fiber. So means if you consider these two rays, they are propagating through the fiber, and at the end, so delay, there will be a delay differences between these two rays, meridional rays and axial rays. If you see here, the both rays are traveling from this input of the fiber at the same velocity and with a constant refractive index of this core. But if you consider that they are reaching to the at another end, they have some delay. Okay, means each rays will reach at this end. They have some delay difference. Why there is a delay difference? Because of that rays are propagating with a different path. Because they are, this one is reflecting, this one is propagating throughout the core here. So that's why these two rays, if you consider at a receiver at this particular end of the fiber, because of the difference in a path length, so that's why they reach with a different time. So if you consider the time taken by this axial rays propagating through the fiber, that will be a minimum. And the time taken by this meridional rays propagating through this path, that will take a maximum time. And that each and every that distance traveled by this particular rays propagating throughout the fiber, that will be depending upon that velocity of that particular rays there. So then we can find out that what will be the a minimum time required by the rays, that is about, we can consider that is about the axial rays. What will be the minimum time required, or we can say that minimum delay, okay. So minimum delay time, and that minimum delay time is depending upon that how much distance traveled by that particular rays with respect to the velocity. Then the distance travel is nothing but the length of the fiber, and that velocity is depending upon that what will be the refractive index of a core. So that's why that velocity is nothing but what, that is about a c by n1, that will be the refractive index of a core. In that case, we'll get that n1 l by c. So this c is nothing but that a light travels in a vacuum. So that is nothing but what, a 3 into 10 to the power 8. That is about the speed. Okay. And this is about a minimum time taken by this axial rays propagating through the fiber, and they travel along with the fiber of a length L. That's why this one is about a minimum time. Then for a meridional ray, means what? This one. They have the critical angle we say. They propagating through the fiber, they travels a distance that is about the same distance L, but with a maximum delay. Okay, because path length are different here. So that's why the maximum delay time. So that's why you can say that is about it. T max, or time taken by the meridian ray to travel the distance L. So that depends upon that L by cos of theta divided by C of N1. Because we say here this is about your critical angle, this one is about critical angle, and this ray that is about acceptance angle, and this one is nothing but a theta. So that's why L, that is about length of the fiber, and cos of theta divided by this particular velocity, that is C by N1. Now T max is equal to what? That is about maximum time taken by the meridional ray to travel the length L. So if you simplify it, that will becomes what? C cos of theta. Okay. Now using a Snell's law, you can simplify it. Using Snell's law, the Snell's law, sine of phi c is equal to n2 by n1 is equal to cos of theta. Then we can write a maximum delay time T max is equal to L n1 square by C of n2. Okay, this belongs to what? A T max and a T minimum. This one is about a T max, and this one belongs to the T minimum. Okay, this one is the term for the T minimum. Now, if you compare that, the delay difference between these two rays, okay, delay difference between these two rays, so we can consider that, or we can obtain the a delay difference between the two rays, and that will become say delay difference, that is del of Ts is equal to T max minus T minimum. So that will be equal to L of n1 square by C n2 minus L, we have the n1 by C. And if you further solve this equation here, while taking that L n1 square constant and a C n2, sorry, if we take a common, so then it becomes what? This L1 square and C n2, that is nothing but a 1 here. And then we have that n1 to the 1 minus n1 here, and we have the n2. Now if you further solve it, we'll get that the equation, that is L n1 square by C n2, n1 minus n2 by n1 here, and is equal to what? L n1 square. This becomes a del, that is about a difference here. That is about a C n2. Because since we know that del is equal to n1 minus n2 by n1. So that is about a delay difference. We are getting the delay difference. But even if we can write, as we say that del is equal to n1 minus n2 by n1, that is approximately. Even we can write that del can be of what? N1 minus n2 by n2 also. If we write n1 minus n2 by n02 here, so then this delay difference equation, that is del of tau s is equal to what? L n1 minus divided by C into n1 minus n2 by n2 here. Then if we solve further, then it will be what? L n1 del by C. So we can write in terms of a numerical aperture, del Ts is equal to L that is about a numerical aperture, that is about n square. We have the twice of n1, that is about a delay difference. So now how this occur? Because we have written earlier that is a numerical aperture in terms of a difference, and that a numerical aperture is in terms of a difference, that is a na. We say that it is equal to n1 into twice of del raised to 1 by 2. So that is about our expression. So if you put that in terms of this one, you'll get that equation in terms of ana. So directly we have written here that degree difference equation in terms of a numerical aperture. So this one is nothing but what? A delay difference in terms of a numerical aperture. So we can say that for a given particular fiber, the delay difference is depending upon that numerical aperture. And that numerical aperture is nothing but the acceptance of a fiber. Delay difference is nothing but the acceptance of a fiber. So what will be the large core area of a fiber? So according to that, that acceptance angle is a large. So that's why the delay difference is again we say it is depending upon that numerical aperture of a fiber. So now we can write using this delay difference what will be the a RMS pulse broadening due to the intermodal dispersion. So that is we can write directly here, that will be L n1 to del divided by 2 under root 3 into C here, and that will be approximately equal to, we can write here L in terms of a numerical aperture also, 4 under root 3 n1, and this is nothing but what? A RMS pulse broadening due to intermodal dispersion. RMS pulse broadening due to the intermodal dispersion. Because we have obtained that the delay differences for a given particular light. So if you compare with respect to when light is propagating through the fiber, then what will be the ideal pulse? So generally we say that that is about a pulse is propagating through the fiber, but in the case of a delay difference we can say that ideal pulse is about a rectangular function with a unit area. So in that case we say that this delay difference we can write the function with respect to your time and amplitude here. And using that, you can find this one is nothing but what? 1 by del Ts. And this one is about 1 by, that is about a del Ts divided by 2. And this is about a del T. So this is about a amplitude here and with respect to time. So if you integrate here, so you'll get that whatever the RMS pulse broadening. So that RMS pulse broadening we have written directly here, and that broadening due to the intermodal dispersion. Now, if you see here that RMS pulse broadening, that will be depending upon that refractive index, or we can say that it will be depending upon that relative refractive index difference, that is about a tau, and again it will be depending upon that length of the fiber. As I told you earlier, that is Again, it is depending upon that what will be the numerical aperture, and that is again different depending upon that relative refractive index difference of the fiber. So to reduce the pulse broadening, so we can reduce the relative refractive index difference as we mentioned earlier. So if you reduce this one, pulse broadening will be reduced. But we doesn't have a scope here. We say that is about a length. Length, if we propagate your signal for the longest length, so instead of that, to decrease length, there is a solution for the length. We can use a repeater there. But if you consider in another way here, so we can decrease that relative refractive index difference for the fiber, so that we'll get that pulse broadening will be small. But how this relative refractive index difference is reduced? Because this one is again depending upon that numerical aperture, and that numerical aperture is again depending upon that acceptance angle of the fiber. So if you reduce the difference, then the acceptance angle of the fiber will change. So then if power launching inside the fiber will change, because numerical aperture is depending upon that acceptance angle of the fiber there. So we have the mechanism here. We can say that reduction of the pulse broadening, or we can say that reduction of the intermodal dispersion by the mechanism of refractive index difference variation, or we can say that length, we can reduce the length of the fiber. So here we can say that there are the different rays are propagating through the fiber. So that's why we can say that there are the various modes are propagating through the fiber. If you reduce the differential attenuation between these particular modes, so we can reduce the pulse broadening, or we can reduce the intermodal dispersion in the given fiber. That is the case for the multimode slip index fiber. But if you consider that, as we say earlier, if we use a multimode gradient index fiber, then intermodal dispersion is reduced. So now we learn here, as compared to the multimode slip index fiber, multimode mode gradient index fiber is good, and they have the lowest intermodal dispersion. So we learn here multimode gradient index fiber. So in the multimode gradient index fiber, that core profile is a parabolic one. So now this one is about your core, this one is about the axis of a fiber, and this one is about nothing but a cladding. Now how your profile looks like? The profile will be what? This one is about a core here. Throughout this one, it is a constant. Okay, this one we have the constant here, but here the refractive index will be maximum at the center here, at this particular axis. Okay, here. Just like a parabolic shape here, so that is about n of r. Sorry, n1 of r, because this one is the n2 now. So n1 of r or n of r. So you can find out how your rays are propagating through the fiber. Based on this, whichever the acceptance angle supporting this fiber, so according to that, your rays are propagating through the fiber. So likewise, this way, your signal, your light rays are propagating through the fiber. because it has the variation in the refractive index profile. Because of that variation in the refractive index profile inside the core, so that's why the rays are propagating with a different velocities, or they are propagating with a different path here. So as we say earlier, that velocity is depending upon that a refractive index. Velocity is depending upon that whatever the refractive index here. So means it is depending upon that refractive index. So in this case here, the variation in the core refractive index, that velocity is changes. So in a multimode fiber, if you consider that the delay differences in the multimode fiber because of that different rays are propagating with a different uh, that we can say different path length here. So there may be a delay difference between the fastest mode and a slowest mode. And for this gradient index fiber, the delay difference we can write that will be a del of dg is equal to L n1 del square divided by twice of c. And that will be approximately we can write a numerical aperture that will be raised to 4 divided by 8 n1 cube raised to c. N1 cube into c. So this one is about a delay difference in a multimode gradient index fiber because a multimode gradient index fiber that co-refractive index is varies with respect to the that at a center it is maximum and gradually it is decreased. So that's why dispersion in the multimode fiber, intermodal dispersion in the multimode gradient index fiber is minimum, and because of that it has a minimum intermodal dispersion, and because of that minimum intermodal dispersion they have the substantial improvement in the bandwidth as compared to the multimode step index fiber. Why it is occur? Because of that various rays are propagating with a different path and all. So different path length because of that index difference, refractive index difference. Okay, so this one is about a path here for the rays. Another rays, this one is about a path likewise. So they have the because that co-refractive index is a varying, so that's why that rays are propagating with a different path here. So if you consider that rays are propagating through the fiber, some of the rays are propagating through the fiber, they are fastest, and some of the rays are slowest here. Because at this core, nearby the core, that rays are propagating near to the axial, or you can say that near the axis of this core, they are propagating slow here. Because that refractive index is high. But the rays are propagating near to the cladding, okay, inside a core here, near to the cladding. The refractive index is small, so that's why they are propagating faster. You can say that there is a slowest and a fastest rays are propagating through the fiber, so that's why the delay difference is depending upon that what will be the refractive index profile. So that's why we can write here delay difference is nothing but the refractive index profile of the fiber there. And then we can calculate that RMS pulse broadening. That RMS pulse broadening, that is equal to sigma, that G stands for gradient index. Here again the G stands for the gradient index fiber, that sigma G is equal to difference in the refractive index, and that a constant D with respect to that a strip index fiber. Or we can write sigma G is equal to, that will be L N1 into del square divided by 20 under root 3 into C. And this D constant, it can be taken between 4 to 10 depending upon that what will be the profile of the optical fiber. So if you draw a graph of a dispersion, intermodal dispersion with respect to a refractive index profile, in that case we can see that at some refractive index profile they have the means that parabolic profile, because this one is about a intermodal dispersion, and we say that, or intermodal pulse broadening. Here it is about a 10 to the minus 2, 10 to the minus 1, this will be a 1, this will be a 10. Okay, likewise. So if you compare here, so at this profile, okay, if you compare, sorry, this one, okay, likewise. So at this profile valued alpha is equal to 2, means gradient index profile will be a parabolic one. Then in that case, that refractive index will be, sorry, that intermodal dispersion will be small, means pulse broadening will be small at a profile of a that alpha is equal to 2. So if that characters index profile alpha is equal to 2, that will be a parabolic in nature. So this will tell you, this equation will tell you what will be the refractive index difference, or what will be the nature or profile of the fiber. According to that, the dispersion will be varies here. So in the case of a intermodal dispersion. So next we consider that, so we can compare here again with what will be the dispersion values for the strip index fiber, then a multimode strip index fiber and a multimode grade index fiber. So as we say earlier, intermodal dispersion for the strip index fiber will be a 0 here, or no intermodal dispersion. But in the case of a multimode strip index fiber, they have the highest intermodal dispersion as compared to the multimode grade index fiber. So next we will learn that a modal noise, or another way to improve that intermodal dispersion, by coupling the modes, and because of that coupling the different mode, the pulse broadening can be reduced. Okay, that is again another way here for the reduction of the intermodal dispersion. Next is about a modal noise. So modal noise is nothing but a, in a particular fiber, that speckled pattern is observed. That speckled pattern is observed in a multimode fiber because of a fluctuation, and because of that particular fluctuations occur, then your characteristics of fiber will changes. So means we say that inside a particular core of a fiber, that speckle pattern is there, and because of that speckle pattern, likewise you can say that's about a speckle pattern likewise. So in that case, due to that particular speckle pattern, so resolution time at the detector will be longer, and due to that it generates the modal noise, or you can say that a speckle noise. Why these speckle patterns are formed inside a multimode fiber? Because at the time of manufacturing, or we can say that when we consider a multimode fiber, and when we consider that light is launching inside the particular fiber at the interface or at the interference of the given particular mode, whichever the sources we are using, that source has the coherence time greater than the intermodal dispersion time within the fiber. So that's why that a speckle pattern occur, or that's why the modal noise will be occur. So that coherence time for a given particular source, that will be depending upon that what will be the width of the particular source. Okay, what will be the frequency width of the source there. So generally a dispersion time we say that is about a del t, and that frequency width we are saying that is in terms of a del f. Then in that case we can write a modal noise that will be is equal to that modal noise that will occur when we have that del f is greater than 1 by del of t. So that is about the condition that modal noise occur, and that modal noise occurs because of that disturbances in a fiber, such as a variation or a discontinuity inside the fiber, or when we are using a connectors, or when we are using a splicing here, or connecting a two fiber there, or when we couple the source to fiber or a fiber to detector here, and because of that there is a fluctuations occur in the speckle pattern, and that's why that modal noise will be generated. So what are the various conditions which gives us the modal noise? Okay, that are the various condition that will gives us the modal noise. So because we can say that a source, we say we have the source, and that source, if you consider that coherent source, they have the narrow spectral width and the long coherence time, or a no, long coherence length. Because of that, that propagation velocity will be different in case of that coherence time. So that's why that generate the modal noise. Then next is about disturbances inside a particular fiber, or a because there is inside a fiber there is a difference in the modes, or there may be a differential modal delay, or a modal or a spatial filtering, or there may be fluctuations inside the particular fiber. So that's why the that modal noise will be present there. Again, there may be a as we say that disturbance inside the fiber, or we can say that there may be a shift in the speckle pattern inside the particular fiber. So that's why that's why that they have the modal noise. So to reduce the modal noise inside the fiber, we need to remove the whatever the disturbances inside the particular fiber, or instead of using a multi-mode fiber, we can use a single mode fiber so that modal noise can be removed here. Or we can use that instead of a narrow spectrum or a narrow spectral width of a source, if we use a broad spectral width or a broad spectrum, so in that case we can reduce the modal noise of a fiber. So that is about a modal noise, and that modal noise, even if you consider that a single mode fiber, that generally we say that it doesn't have, because single mode fiber doesn't support that difference in a mode, so that's why the single mode fiber doesn't have that modal noise. But a single mode fiber, in a single mode fiber, that modal noise can be present because they are supporting the two different fundamental modes, and that fundamental mode supports with the different in terms of that polarizations and all. We'll learn that polarization part. So we could just say that only multi-mode fiber they have the modal noise, and single mode fiber they doesn't have the modal noise. Next is about a overall dispersion. So overall dispersion of a fiber, if you consider that multi-mode fiber, that pulse broadening, or you can say that overall dispersion, that will be is equal to sigma t is equal to sigma c square plus sigma n square. That is about a sigma c is nothing but intramodal dispersion, or we can say that is about a chromatic broadening or a chromatic dispersion, and sigma n is nothing but the intermodal dispersion. This one is about intramodal, and this one is nothing but a intermodal dispersion. And so we can find out that intermodal dispersion and intramodal dispersion